Lesson 10, Digital Electronics and Microcontrollers. Hello folks, welcome to an exciting journey into the world of digital electronics and microcontrollers. In this lesson, we'll cover the basics of digital electronics, delve into microprocessor architecture, and explore the nuances of digital system design and programming. Our aim is to provide you with a comprehensive understanding that you can actively apply in your professional pursuits. Introduction to digital electronics and microcontrollers, for example, logic gates, microprocessor architecture. Digital electronics is the foundation of modern electronic systems. Unlike analog electronics, which deal with continuous signals, digital electronics works with discrete signals, primarily binary code. Let's explore some key concepts. Logic gates. Logic gates are the building blocks of digital circuits. They perform basic logical functions that are fundamental to digital circuits. Here are the primary types of logic gates and gate. Outputs true only if all the inputs are true. Or gate. Outputs true if at least one input is true. Not gate. Outputs the inverse of the input, also known as an inverter. NAND gate. Outputs false only if all the inputs are true, inverse of AND. NOR gate. Outputs true only if all the inputs are false, inverse of OR. XOR gate. Outputs true if an odd number of inputs are true. XNOR gate. Outputs true if an even number of inputs are true, inverse of XOR. Activity. Try creating a simple circuit using a few logic gates on a breadboard or using simulation software. Explore how changing inputs affects outputs. The binary system. The binary numeral system is at the core of digital electronics. It uses only two symbols, 0 and 1. Computers use binary to process data and execute instructions. Let's convert a decimal number base 10 to binary base 2 to illustrate. Decimal, 13, binary, 1101. Exercise, convert the following decimal numbers to binary, 5, 18, 34. Microcontroller and microprocessor architecture. Microcontrollers are compact integrated circuits designed to govern specific operations in embedded systems. They combine a microprocessor, memory, and input-output peripherals. Here's an overview of their architecture. Core components of a microcontroller. CPU Central Processing Unit, the brain of the microcontroller, executing instructions from programs. Memory. ROM stores firmware or permanent instructions the device runs upon power-up. RAM. Temporary storage for data that can change during operation. Bus. A communication system that transfers data between components. I/O ports, interfaces through which the microcontroller interacts with external devices. Application. Consider examining the architecture of popular microcontrollers like the Arduino or Raspberry Pi to see these components in action. Understanding digital system design and programming. Digital system design involves creating systems that manipulate, store, communicate, and display information. Let's examine the steps involved in designing a digital system. Specification. Define what the system is supposed to do. Architecture design. Determine the overall structure and workflow of the system. Component selection. Choose appropriate components like microcontrollers, sensors, and ICs. Circuit design. Develop schematics that represent the connections between components. Prototyping. Build and test a prototype to validate the design. Verification and testing. Thoroughly test the system to ensure it meets specifications. Challenge. Design a simple digital clock using a microcontroller. Define its features, select components, create a schematic, and simulate the system operation. Programming microcontrollers. Microcontrollers need to be programmed to perform tasks. Programming often involves writing code in languages like C or Python. Here's a basic outline of a microcontroller programming process. Developing a program. Write the code. Use an integrated development environment IDE to write the program code. Compile the code. Convert the code into machine language that the microcontroller can understand. Upload to microcontroller. Transfer the compiled code to the microcontroller's memory. Debugging, test and fix any issues in the program. Quick test project, write a program to control and LED using a button press. Start by writing a pseudocode, then proceed with actual coding and testing on a microcontroller platform. Executive summary. Here's a comprehensive summary of digital electronics and microcontrollers. Digital electronics. Digital electronics involves the use of electronic circuits to process and manipulate digital information. The key characteristics of digital electronics are: 1. Binary system. Digital electronics uses a binary system where information is represented using only two digits, 0 and 1. 2. Discrete signals. Digital electronics deals with discrete signals, which are signals that have only two possible values, high 1 or low 0. 3. Logic gates. Digital electronics uses logic gates, which are electronic circuits that perform logical operations on digital signals. Microcontrollers. A microcontroller is a small computer on a single integrated circuit IC that contains a processor, memory, and input/output I/O peripherals. The key characteristics of microcontrollers are: 1. Processor. Microcontrollers have a central processing unit CPU that executes instructions and performs calculations. 2. Memory. Microcontrollers have memory, which stores data and program instructions. 3. I/O peripherals. Microcontrollers have I/O peripherals, which allow them to interact with external devices and systems. Applications of microcontrollers. Microcontrollers are widely used in many applications, including: 1. Robotics. Microcontrollers are used in robotics to control motors, sensors, and other devices. 2. Automotive systems. Microcontrollers are used in automotive systems such as anti-lock braking systems, ABS, and engine control units, ECS. 3. Medical devices. Microcontrollers are used in medical devices such as pacemakers and insulin pumps. 4. Consumer electronics. Microcontrollers are used in consumer electronics such as smartphones, tablets, and smart home devices. Programming microcontrollers. Microcontrollers can be programmed using various programming languages, including: 1. Assembly language. Assembly language is a low-level programming language that uses symbolic codes to represent machine-specific instructions. 2. C programming language. C is a high-level programming language that is widely used for programming microcontrollers. 3. Arduino. Arduino is a popular platform for programming microcontrollers using a simplified version of the C++ programming language. Here's a comprehensive summary of understanding digital system design and programming. Digital system design. 1. Digital logic. Understanding digital logic gates, Boolean algebra, and logic circuits. 2. Combinational logic. Designing combinational logic circuits using logic gates and Boolean algebra. 3. Sequential logic. Designing sequential logic circuits using flip-flops, counters, and registers. 4. Digital circuit analysis. Analyzing digital circuits using timing diagrams, logic analyzers, and oscilloscopes. Programming. 1. Programming languages. Understanding programming languages such as VHDL, Verilog, C, and Python. 2. Algorithm design. Designing algorithms for digital systems using flowcharts, pseudocode, and programming languages. 3. Microcontroller programming. Programming microcontrollers using assembly language, C, and other programming languages. 4. Digital signal processing. Understanding digital signal processing concepts such as filtering, convolution, and Fourier transforms. Digital system design tools. 1. Hardware description languages, HDLs, using HDLs such as VHDL and Verilog to design digital systems. 2. Computer-aided design CAD tools, using CAD tools such as Xilinx ISE, Altera Quadus, and Cadence Virtuoso to design and simulate digital systems. 3. Simulation tools, using simulation tools such as ModelSim, QuestaSim, and VCS to simulate digital systems. Best practices. 1. Modularity, designing digital systems using modular design principles. 2. Reusability, designing digital systems using reusable components and modules. 3. Testability, designing digital systems with testability in mind. 4. Documentation, documenting digital system designs using clear and concise documentation. In conclusion, understanding digital electronics and microcontrollers lays the groundwork for developing innovative digital solutions. This lesson covered critical concepts, including logic gates, microcontroller architecture, digital system design, and programming. Armed with this knowledge, you can approach digital projects with greater confidence and creativity. As you continue to explore these subjects, remember that practical application and experimentation are key. Engage actively with components and code, and always be curious about how things work beneath the surface. Thank you for attending today's lecture. Hope to see you again in the next lesson. Happy learning, folks!